Lovely. So to follow on from yesterday's lecture where I introduced rocks and the 3 different types of rocks, I'm now going to talk for the next 2 lectures in a little bit more detail about igneous rocks, which for many people are the most interesting type. I'm more of a sediment person myself, but they are really interesting, especially in the South Pacific, where essentially most of our islands are volcanic islands. So we're sitting on igneous rocks, or islands made out of igneous rocks in the majority. And they also form some spectacular scenery. So you don't even need an active volcano to produce spectacular scenery. This is a wonderful rock called shiprock, and it's in the States. And what that is the old inside of a volcano. The outside, with all the volcanic ash and the lava being worn away to reveal the volcanic plug. So this is made of an igneous rock that once solidified in the inside of a volcano. And this here is what we call a dike. So when magma penetrates cracks or forces its way through existing rock, this one perhaps fed that volcano, and then it solidifies, we call it a dike. And this is an example of a dike that's not being eroded as fast as the surrounding rock. And it produces really, really lovely scenery, which we have a lot of in the South Pacific as well. Just to give you some other spectacular examples, you can see this in Fiji, we'll see it on the field trip. Not this particular example. This is an example of columnar jointing. So if a lava flow cools in a regular pattern, the lava flow is has an even thickness, and it cools in a similar rate throughout the lava flow. Quite often, you get these beautiful jointing patterns. This is again in the USA. We see this in Fiji as well. Obviously, we have our active volcanoes. Our igneous rocks that form underground from slowly solidifying magma. In some instances, they produce these huge bodies of igneous rock called batholiths. I'll introduce all these in the next couple of lectures. And if those are uplifted to the surface, they too can produce some really dramatic scenery if they're eroded, because they're incredibly hard in a lot of cases. This is Yosemite National Park. This whole area here is a huge batholith. Made out of a rock called granite or dacite, or diorite, sorry. And this place here has since eroded this valley, and now they've melted. We're not in the glacial state anymore. We use this really famous rock, the Parkdome. And just a more local example, I introduced this in the previous lecture. This is a scenery you see from Suva Harbour, and this is Josky's Thumb. Made famous by Sir Edmund Hillary, who was the first man to climb Everest, who famously was part of he used to work down in Fiji because he was in the Air Force, and Noah campus used to be an Air Force base. And he tried to climb Josky's Thumb, and he failed, and then he climbed Everest and succeeded. So he always calls this his training for Everest. He since went back and climbed it, but anyway. It's actually on the $10 bill as well, not Josky's Thumb. But this is the inside of an ancient volcano as well. I think it's about a 3 million year old volcano. And all of this landscape here was built up by the volcanic activity. All igneous rocks. So some statements I've already introduced to you. Igneous rocks form from liquid rock, from magma. So they form from liquid rock that has solidified, crystallized to form a solid, which we call an igneous rock. They can crystallize within the earth to produce intrusive igneous rocks. Literally, they've intruded in the earth. Or they can be erupted as lava. The magma can be erupted as lava, where it solidifies more quickly to form extrusive rocks on the Earth's surface. And these are 2 major distinctions when we talk about igneous rocks. So I realise my microphone is not working. Try different places. There. So these are the topics we're going to cover in today's lecture. We might not have time to get to the end, but I'll just continue on Friday. But first we're just going to talk about how we classify these igneous rocks. The main 2 ways we classify them are texture and composition. So I'll introduce you to some terms that you'll be using next week in your labs. I'll talk about how the magmas form if I have time right at the end. And just to give some other photos, the field trip we're going to go on And in the mid-semester break, we're going to do a tour around Ritty Level. We're going to see this. This is near Raki. This is, again, the inside of an extinct volcano. And this is some of the preliminary jointing that we'll see on the picture. Two of the things we'll see. So just if you look at some of these pictures here, these are all close-ups of different types of igneous rocks. And as you can see just by the colour and the minerals that are contained within all those igneous rocks, there's a big variety of igneous rocks essentially. So we need some way of classifying them into different categories. This is from near Raki as well. And this is from I've got some examples of this rock here. This is from a beach down the road. And these are the two main ways that we classify igneous rocks. So to do with their texture and to do with their composition. Because most igneous rocks, they're not glassy, they actually do contain minerals. You'll see the term mineralogy used. If you describe a rock's mineralogy, you're describing the minerals that make up that rock. So first of all, if we're going to talk about textures, the two basic descriptions we use for texture are whether the rock is coarse-grained, so can we see individual crystals in that rock? The term that we use and you'll use in your lab is phaneritic, which literally means visible. But I'll just talk about coarse-grained here. Generally, when we talk about coarse-grained rocks, we're talking about rocks where we can see the crystals in this interlocking mosaic. And the crystals generally several millimeters in size. And these rocks are formed from magma that cools slowly, that should be there. So this is underground. Any rock that's extruded on the surface is cooled quickly. So if it's cooled slowly, if it has large crystals, it must have cooled underground. It's an intrusive rock. And this is a nice example here of a granite. Fine-grained rocks, we know that magma that formed these rocks must have cooled quickly. So we know these are extrusive rocks. The only microscopic crystals are present. And generally speaking, we can't see the crystals with the naked eye. So aphanitic is the term we use, and you can't see them, aphanitic. But under a microscope, you can see the crystals. And people have done experiments, even back in the day before we could do these complicated lab experiments. Geologists went out, they observed what happened when lava was erupted at the surface and cooled quickly, and they looked at the rock left behind, and they saw rocks with very, very small crystals. A man called Bowen, who I'll talk about later, he was quite famous in the geology world. He did extensive laboratory experiments where he had these furnaces that were heated to incredibly high temperatures, high enough to melt rocks, and then he cooled them at different rates, and he saw what happened, and exactly what I just described happened. If they were cooled incredibly slowly, so he didn't even see the finished product because they cooled that slowly, but he could watch the process of nucleation. You got these big crystals, when they were cooled quickly, you got these small crystals. And this is an example of something you'll be doing in your second year if you take ES106. So this is just a hand specimen of granite. So this is a coarse-grained igneous rock. This is basalt, a fine-grained igneous rock. And what geologists do is they get a piece of rock, and you can stick it to a glass slide, polish it down to 30 microns, so incredibly thin. So it's stuck in resin onto the slide, and then you shine polarizing light through it in a microscope. And if you shine crossed polars, anyway, we'll get into it now, the way that the light refracts, or mineral refracts the light and produces colour can tell us a lot about the mineral. And also it allows us to look at, in finer detail, the crystal patterns, the texture of igneous rocks. So this is a very big close-up of a granite with these huge crystals. Irregular surfaces, remember I told you it's very rare to get these perfectly formed crystals. And basalt, you can't see the crystals with your naked eye, but if you look under a microscope you can see these tiny, tiny crystals. So that's why microscopes are incredibly interesting. If you want to see what a thin section looks like under a polarizing microscope, I can show you in the lab if you like. I'll set my lab for you. So just to talk a little bit more detail about these extrusive and intrusive rocks, And I've given you an example here of a volcano. There are other situations where you can have magma produced, but this is a nice example. So I've removed some of the ground for you. So we have a volcano at the surface, a magma chamber down here, the vent, so this is the volcanic vent, and this feeder dike. So the magma is fed through this channel here to the volcano. So our extrusive rocks, so rocks that form on the Earth's surface, you can loosely divide them into pyroclastic rocks. So these are rocks made from material that is being erupted, thrown out of a volcano. Okay? I'll go into this in a bit more detail now. So whether that's volcanic ash or blocks of rock that have been thrown out of a volcano, we call them pyroclasts or pyroclastic sediments. And once they settle on the Earth's surface and they're buried, they form rocks which we call pyroclastic rocks. And where that lava is erupted out of a volcano, well, that magma is erupted and flows down the side of the volcano. That's our lava. So we get these nice layers or tongues, they're like tongue shaped, going down the volcano of lava, which is molten rock, which solidifies to form an igneous rock. So our intrusive rocks, we generally speak of plutonic rocks when we talk of intrusive. So these are ones that form quite deep in the crust, so they cool slowly. There's another type of intrusive rock called hypoabyssal igneous rock, which forms at very shallow depths. And actually, because it forms at quite shallow depths, it sometimes looks a lot like these extrusive rocks because it cools slowly, so it has these small crystals. So we often join these with the extrusive rocks because there's so many in the surface. So usually, people use the term plutonic and intrusive interchangeably. We're talking about these deep igneous rocks down here. So just to go through them a bit in turn, I'm going to try a different place. So first of all, our pyroclastic rocks. So we can divide them loosely. There are lots of different categories. I'm going to describe three for now. So I'll first describe our volcanic ash, which I've all seen pictures of this. When a volcano erupts, it's this big cloud of material that is erupted with it. This is a feature of explosive eruptions. Not all eruptions are this explosive. You get this big cloud of ash. And if you look at that ash closely, it tends to be made up of tiny, tiny fragments of glass. So molten material, tiny droplets of molten material that hasn't had time to form crystals. So it forms this amorphous solid called glass. So you can see here, there's lots of tiny glass shards. You sometimes get crystals blown out of a volcano, so you actually perfectly formed crystals that are formed deeper in the volcano and now they're being blown out. And tiny rock fragments. So, yeah, there's generally a mixture. There's some rock fragments here. There tends to be a lot of glass. And this, when it's buried, these get welded together, cemented together to form a rock called a tuff. So this is a rock formed from volcanic ash. The volcanic ash is no longer loose, it's a solid. And here's some beautiful cliff faces. Again, this is in the States. And each of these layers is made up of volcanic ash. You can get huge thicknesses of volcanic ash producing this rock that looks like that. And some of the ash has bigger fragments in it. So this is a close-up of a quarter tuff. Tuff is also the name of a really, really terrible heavy metal band I discovered when I was writing this lecture. Don't be confused. So we also get things blown out, much larger chunks blown out of a volcano, so much larger than the volcanic ash. And any molten material, so molten rock that gets blown out of a volcano, so a blob of magma, it'll fly through the air. The surface will start to solidify, it will land on the ground, it will solidify, but still in quite a big lump, and we call them bombs. They're often quite streamlined because as they're thrown out of a volcano, they stretch out in the direction that they're travelling. And this is an example of a bomb, of bombs being thrown out of this volcano here. And so quite often in volcanic rocks, in pyroclastic rocks, we get these large blocks because the bombs landed in the volcanic ash after an eruption. So here's a close-up of one which shows a nice streamlined pattern. Sometimes on the edge of these bombs you get volcanic glass. This is a volcano where you can see all these bombs hitting the ground. This is a group of students in the States on a field trip, and a bomb narrowly missed them. So this was thrown out of a volcano. Some people standing there. So yeah, a few meters over. That wouldn't be good. This is a holiday photo of mine from Sicily, in Italy. And that's a nice example of a true volcanic landscape. So the ground was completely made up of volcanic ash, with these big volcanic bombs sitting on it. And I've told you that tuff, so volcanic ash settles in layers. And this is a nice example of in Fiji where you can volcanic bomb hit the layers and make a little depression in the surface, and then ash will continue to accumulate. And just before I move on, if you walk up the Father Bay Road or anywhere in Suva, in fact, whenever there's rock exposed, it's this pale grey rock. So it's actually a deep sea rock. It contains loads of beautiful macrofossils. But every so often you see these darker bands in it. You'll see it again if you walk up the Father Bay Road. And the darker bands stick out a little bit. And then if you look at them under the microscope, maybe I'll set this up for you, they're volcanic ash. So basically 3 to 5 million years ago, when that rock was forming in the deep ocean, so sediment was raining down, microfossils were dying, settling to the sea. The volcanic ash from the volcanoes near Bar on the north of Italy levee was also settling out in the ocean. And you get these nice dark bands from whenever there was an eruption. So each one of those bands represents an eruption. It's quite nice. So another really distinctive type of pyroclastic rock is called pumice. You might have seen it, you use it to rub hard skin off their feet. And this forms because lava, or magma when it's underground, contains dissolved gas and sometimes a lot of water. So just a simple experiment of having a Coke bottle. So when that lid is on the Coke bottle and the seal isn't broken, the Coke is under pressure and you can't see bubbles in it, right? That's because when a liquid is under pressure, it can dissolve more gas. It's the same with magma. So when this magma is underground, it has a lot of gas dissolved in it. As soon as it's erupted and the pressure is released, the gas comes out of the liquid. And sometimes, when the liquid solidifies, those air bubbles are preserved in the liquid. So when you have a lava, which has a lot of water and a lot of gas in it, what happens is you get a type of froth. You know when you're doing your washing up and you get your nice bubbles on the top because of the soap? It's actually similar in lava, similar in volcanoes. And when that froth solidifies, you get a nice rock called pumice. I've got some here, I won't pass it around because I've only got 5. But the distinguishing features of pumice are that it's incredibly light. And it actually floats. And if you look at any beach around Fiji, or if you're from the Solomons or Vanuatu, you'll see a lot of this washed up on the shore. That's where I got it from. So there's these bits of pumice that have been eroded by the sea, so they're nice and smooth. And this, who knows where this came from? It could have come from Tonga, it could have come from anywhere, but because it floats, they're quite often washed up on the seashore. But something that's really nice, I think is really nice, quite often when you have a volcanic eruption, you get these huge rafts, so these floating piles of pumice. And eventually they might get waterlogged, and they might sink, or they might float, disperse, and hit another island. But this is a new island formed in, I think this is the one that was formed this year in Tonga. I think that's where this photo is from. So a new island is formed by a volcanic eruption. And you can see here, there's an eruption from this island as well. And it's released this raft of pumice. That's made up of small pieces of rock with these air bubbles in them. So yeah, if you want to see what after the lecture, come and have a look. And we call these bubbles, so air bubbles that are trapped in an igneous rock, we call them vesicles. You might have heard that term in biology as well. So plants and animals, or plant tissues have vesicles sometimes. It just means an airspace, and we use that in geology as well. So moving on now to our lavas, so our extrusive igneous rocks formed from lavas. They cool slowly and they're fine-grained. I've already told you that. When we talk about composition in a second, you'll see why composition in lava is incredibly important, because it produces very different styles of volcanic eruption. So one type of lava is rich in magnesium and iron, and that produces a very ruddy, so low viscosity lava called basalt, which solidifies to form a rock called basalt. Other types of lava we call felsic. They have very low magnesium and iron, very high sodium, silica, potassium, and they're incredibly sticky, and with them you get the very explosive volcanic eruptions. They produce a lava, extrusive rock called rhyolite. I'm coming back to these rock names now. And lava flows out in layers, so where they build up over time, and maybe then they're eroded so we can see them, and they produce these nice layered rocks. And quite often what you see, you'll get alternating layers of lava and tuff, and lava and tuff. Because you can imagine a volcanic eruption, you get lava spewing out, volcanic ash spewing out, and it takes a while for that ash to settle down. So that's one eruption. So the next eruption will spew out lava on top of that volcanic ash will spew out, etc. So quite often you get alternating layers. And this is a really beautiful, I've never been there, and piece of scenery in India. There's huge, huge expanses of just layers of basalt lava in India, and it coincides with the timing of the extinction of the dinosaurs and the mass extinction that went on at the time. So for a long time it was thought that these huge volcanic eruptions in India spewed out so much gas, they changed the climate, and that's why the dinosaurs. That isn't the favourite theory now, but for a long time it was up there in one of the hypotheses. And just like our pumice can contain these bubbles called vesicles, so can lava, for the same reasons that pumice contains vesicles. Lava's a bit more sticky than that frothy stuff that forms pumice, so quite often those bubbles, those air bubbles, get stuck in the lava, and when the lava cools, they're preserved. And sometimes, when water passes through that lava, many years later, or millions of years, they can precipitate minerals in the vesicles, and we call these amygdales. Don't worry about that. Just remember the vesicles. We'll see a lot of these in the field trip, these amygdales. They're formed from these air bubbles. And actually, when the people who went to the moon and brought back samples, the particular samples they brought back were this rock called basalt with vesicles. So this is a microscopic view of moon basalt, which has these air spaces in it. Quite nice. We know that there was lava flowing on the moon at some point. So intrusive rocks, these cool slowly. They can form down here as the magma is injected into cracks in the subsurface, or actually it pushes its way through the rock, forming cracks as it's under pressure. They can form down here in these big magma chambers, and they cool a lot more slowly than this erupted lava, so they're fine-grained. Coarse-grained. And again, we have different names depending on the composition. So the same magma that forms basalt, there's iron, magnesium-rich magma. If it cools underground, we call it a gabbro, where we can see big crystals. And the same for felsic magma. If it cools slowly underground, that's where we get a granite. This is a terrible photo, but this is from quite near where I live back home in a place called Cornwall. There are huge cliffs formed of really nice granite, and they have these really large crystals in them. So I've told you about coarse-grained and fine-grained rocks. There's a third category. We call these porphyries. So they have porphyritic texture. So this is where you have actually two crystal sizes. There's usually a much finer-grained, what we call a ground mass, so background, but it might have much larger crystals floating in it. We call those crystal sphenoclists. So okay, we have fine-grained and we have coarse-grained in the same rock. How does that happen? Basically because of this. So you have a magma that starts cooling underground. So the crystals with the highest crystallization temperature, the lowest melting temperature, will start to crystallize first. So you you'll have magma with these crystals growing and growing and growing, and the rest of the magma is liquid. What if that magma is then erupted? The rest of the magma will cool very quickly and have very fine crystals. So basically, where you see this texture, it's very, very common where you have volcanic scenery, because you have these magma chambers sitting underground, the crystals are growing, they're erupted. Most of the rocks you see in Fiji actually have this texture because of this situation. But it might be that you have a magma down here, building very slowly, and it's just pushed up a bit. So the next crystals are not quite as big, but they're still quite big. But the most common situation is under a volcano, where you have a magma chamber, crystals start forming, it's erupted, and only microscopic crystals can form. This is a simple cartoon of the tones we use. So the background is called the ground mass, and those larger crystals, which often have quite nice crystal faces, they've had a lot of time to develop the crystal faces. They're not competing with other crystals because they're floating in a liquid. We call it crystals. And there are many different combinations of minerals and rock types. This is a nice andesite. Lots of this in Fiji, with some nice warm blend crysts. This is actually an example where the ground mass is quite coarse-grained, but it does have much larger plagioclase crysts in it. The granite, lovely crystal faces, and basalt quite often has a type of feldspar as phenocryst. This had a very high concentration of phenocryst. And I've got some rock samples here from Raki. I'm sure you're not supposed to take rocks from beaches, so don't tell anyone what I did. At my friend's house, I've got some examples of this porphyritic texture in the rocks here, and you'll see it in the lab as well. Okay, so moving on from texture, we're now going to talk about the composition of the igneous rocks and how we classify rocks according to that. So we mainly classify the composition feature by the amount of SiO2 contained in the magma. So it's not present as quartz, it's just how much silica and oxygen in that ratio in total is in that magma. Okay? And most magma has between 40 and 70% silica. And there are two main compositional groups. There are groups between these. We have our felsic groups. And they have a lot of silica in them. These are the magmas that are very sticky. They don't flow very easily. And these are the ones that form our explosive eruptions. And we also have our mafic magmas. So rocks formed from mafic magmas are mafic igneous rocks. And these are poor in silica. They have very low silica content. And they come, you can just remember them. So that's the symbol. So here we have feldspar. These igneous rocks have a lot of feldspar and a lot of silica. These igneous rocks have a lot of magnesium and a lot of iron. So Fe is iron. That's why they use it. So felsic magmas and the rocks, felsic igneous rocks, tend to be light, pale in colour, because most felsic minerals are pale in colour and colourless. So typical minerals in felsic rocks are quartz, which some of you will have seen in your labs, is colourless. Two different types of feldspar. The most common is autoclase feldspar and muscovite mica. We do get some biotite mica as well in some circumstances, and these aren't the only minerals you'll see here, but these are the main minerals. And if you remember your silicates, you'll notice that most of these minerals are framework silicates, so where the silica tetrahedra are joined at the borders, or they're sheet silicates, where they're joined in 2 dimensions but not between the legs. So mafic igneous rocks tend to be dark in colour. This is because they contain a lot of iron and magnesium. They tend to be a lot denser because those elements are denser. And they contain, these are really common minerals in your mafic igneous rocks. So olivine, which is actually green usually, pyroxenes, amphiboles, so your hornblende, and a biotite mica. So you won't find muscovite mica, this is your colourless mica, in mafic rocks. You'll find biotite mica. And if you'll notice, most of these minerals, you'll notice they're all silicates for a start, but they're mostly chains and isolated tetrahedron. And I'll talk around this diagram for quite a while because it's a really nice summary diagram. So if you look at this chart to begin with, so on this side we've got our felsic group. In between mafic and felsic, we have a group called intermediate. It's got intermediate content of silica, intermediate concentrations of iron and magnesium. And the mantle is made up of ultramafic rocks. So they have even more iron and magnesium and even less silica. But we don't find many of them on land. So these are our distinctions. And along this side of the chart is the percentage of a mineral. And we've got nice minerals outlined in this chart. So in this case, in a granite, you might get anything between 40 and 15% orthophase feldspar. Definitely about 20% quartz all the way through, minimum. Might get some plagioclase feldspar, but you mostly got orthophase feldspar. Muscovite mica, maybe a little bit of biotite mica, and some hornblende. As you move across into more mafic rocks, our intermediate group, they have a lot less quartz. They have some quartz. This is because they have a lot less free silica. So they can't form quartz. The silica will go into other minerals in combination with cations instead of being free as quartz. We have some orthophase feldspar, but by far and away, the most common feldspar is plagioclase. Bit of muscovite mica, increasing amounts of biotite, and a lot of amphigold, so our hornblende. When we get into our mafic rocks, any feldspar present is plagioclase. These minerals you'll see in the lab a lot more. I know you haven't seen them yet. You've seen feldspar, but not the different types. But no orthophase feldspar. We start getting a lot more pyroxenes and a lot less hornblende. And you might even get a little bit of olivine. Ultramafic rocks are purely made of pyroxene and olivine. That's what the mantle is made out of. And the trend going from felsic to ultramafic is from high to low silica content. And other really important trends are, okay, so these have more sodium and potassium than the mafic rocks. So imagine you have a magma. So, okay, iron, magnesium, and calcium increases this way. So say you've got a magma, and you have a lot of sodium and potassium, but not much iron, magnesium, and calcium. You can't form an ultramafic rock because the ingredients aren't there. So these rocks are sodium rich, these rocks are much more denser metal rich. And another really important thing is these magmas, we've got magmas that form felsic rocks. They form at a lot lower temperatures than these. So these contain minerals that can crystallize at much higher temperatures. So these represent much hotter magmas. And because the mafic and ultramafic rocks contain more dense elements, the density of these rocks is greater. And something I'll come on to in a second is viscosity. I've already talked about that before. That's the stickiness of the lava, of the magma. These magmas are a lot stickier than these. But they're the basic trends. And the reason you get more orthophase feldspar and plagioclase over here is that is because it contains a mineral with lots of potassium in it. Whereas plagioclase has a lot more sodium and calcium, so you need calcium to form. So the types of minerals you find are to do with the composition of the magma. I go back a bit. And you'll see at the top, as soon as we started chemically analysing rocks, we discovered that rocks that looked incredibly different. So a granite, which is coarse-grained, and a rhyolite, which is very fine-grained, you can't see the crystals, they can have exactly the same chemical composition. So essentially, if you have a magma with this composition, if it cools slowly, you'll form rhyolite. If it's granite, if it cools slowly, you'll form rhyolite. So these rocks, they're different rocks, they look very different, they have very different textures. And there are lots of different other names, so this side of the intermediate field, the extrusive rock, the lava will be called the dacite, but if it's coarse grained, we call it a granite diorite. So andesite, which is the rock I've got with me, it's called andesite if it's a lava, if it's an extrusive rock, or diorite if it's coarse grained. We have basalt and gabbro over here. And it's very, very rare for these rocks to reach the surface, or these magmas to reach the surface, so we don't really name the extrusive equivalent, because there isn't really one. There are a few, but they're not very common. They've all come out of perspective. And just to show you how different they look, so our felsic equivalents, these have the same composition, these have the same composition, these are extrusive, and these are intrusive. And as you can see, just as a first test when you're looking at an igneous rock, you can look at the colour and say whether it's felsic, intermediate, or mafic, just by the relative proportions of light to dark minerals. So granite, so felsic rocks, will have a much higher proportion of light minerals to dark minerals. Intermediate rocks will be roughly equal, whereas mafic rocks have a much higher proportion of dark minerals. And in the fine-grained equivalents, they just get darker in colour. There are exceptions, but that's the main rule. And just to show you what a peridotite looks like, so this is our ultramafic rock that makes up the mantle. It's purely made up of olivine and pyroxene, maybe a few other minerals in there as well, but it's usually 90% olivine. It forms these really distinctive greenish rocks because olivine is green. This is what the mantle is made up of. So now just to introduce a few reasons why viscosity is important. This is a graph showing viscosity on this scale, measured with Poisson. So just an example of a very low viscosity fluid, so water, it flows very easily. If you put it on the floor, it will spread out quite far. Olive oil, slightly more viscous. Ketchup, a lot more viscous. Basalt lies around here, so it has a low viscosity. Andesite lava has a slightly higher viscosity, and rhyolite lava, so felsic lava, is up here. And just to look at this graph, you'll see that basalts, the rhyolite here, dacite, andesite, basalt, they're much higher temperature. Lavas got much lower viscosity. Whereas rhyolite, they're much lower temperature. Lavas, magmas, but much higher viscosity. So, in our lecture on volcanoes, I'll introduce this in more detail, but where you have mafic lavas being erupted in a volcano, because they're very low in viscosity, they'll spread out quite far, and there are two very distinctive types of volcanoes formed where you have basalt. So these are the types of volcanoes that are common in Hawaii, because the lava is basalt. And you can see they have very, very low angle sides, and that's because the lava, when it erupts, it spreads out quite far. So underneath here, there'll be layers and layers, thin layers of basalt lava. And another type of volcanic eruption with basalt in it is a fissure eruption, and this is simply where you have a crack in the ground, and basalt, because it's low viscosity, if it's under pressure underground, can erupt through the crack. So you get these long, narrow eruptions. But the lava still spreads out either side quite far in very thin layers. If you have volcanoes with felsic lavas, so these have very high viscosities, because those lavas don't flow very easily, they tend to move very, very slowly through the vent, and pressure, incredible pressure, can build up behind those lavas if there's pressure coming from the ground. And quite often, because they move very slowly, they solidify, they crystallize here in the vent, and then the force of gases and lavas from underneath, again, puts a lot of pressure inside that volcano. When they do erupt, because they're not very good at flowing, they tend to form these very steep-sided volcanoes. Because they can't flow out very far. But But when they erupt, they're incredibly explosive. This is Mount St. Helens, which erupted in 1980. This is in the States. This is before and this is after. The eruption, which was even more explosive than that, literally blew the side and the top of the eruption of the volcano because of all that pressure building up inside the volcano. And these are incredibly dangerous. So now I think I've got time. I know that's not right. I've got 10 minutes or so. So how do we form magmas? I'll talk about this a bit more next time. Where do rocks melt? How do they melt? We know a lot of this through lab experiments, through computer models, and through Earth observations. So it's all really down to the melting temperature of that rock. So if you heat, or if you cross that line of that melting temperature, then you can melt any pre-existing rock. But actually this melting temperature depends on lots of things. So it depends on its composition, what it's made out of. Different minerals melt at different temperatures. But also the ambient conditions. So what the temperature and pressure conditions are, how much water is present. So this is a diagram, I'll go through one of these in turn. So where you have situations of high pressure, you have higher melting temperatures. So things are more likely to be solid. You release that pressure, your melting temperature decreases, and maybe you can melt at a lower temperature. It's easier to melt that rock. The opposite is true of water. You have a low amount of water mixed with your rock. It has a high melting temperature. But the more water you have in that rock, the lower the melting temperature. And as I've already told you, mafic rocks have minerals in them that have a much higher melting crystallization temperature, so you need a lot more heat to melt the felsic rocks. And this is really important. I probably need about 15 minutes and I don't have it to discuss this. But this man called Bowen, who had his furnaces, he had his magma, and he watched what happened when you cooled his magma slowly. He noticed that different minerals have different melting temperatures, crystallization temperatures, depends which way you're coming. And actually, we had this series called Bowen's reaction series as a result. So here we've got high temperatures. So olivine can crystallize or melt at a much higher temperature, depending on whether you're heating or cooling. So it is your calcium-rich cladding phase. And this is the order of minerals. So take it the other way. Okay, lower temperatures. You start melting a rock that contains all the base feldspar. Because its melting temperature is down here, they'll start to melt. The other minerals in the rock, if they're present, won't melt. But this will start to melt. The next mineral to melt will be mica, then quartz, systematically up the system. So what this means is when you have a rock and you melt it, you never really fully melt it. Because you might have enough heat to melt these minerals, but not all of them. And the analogy I give is if you put a chocolate chip cookie in the microwave, the chips will melt, but the rest of the cookie won't. And that's because the rest of the cookie has a different melting temperature than the chocolate chips. So we talk a lot, we will next week talk a lot about partial melting. So most magmas are formed from a rock which partially melts. It might only melt 1%, it might melt 20%, but it's quite rare to melt the entire rock. And so if you have a situation in the Earth, you might have some droplets of liquid in a solid mass, and the ratio of liquid to solid depends on the situation and how many minerals you can melt. I'll talk a lot more about that next time. And I probably won't have time to do all this, but okay, just to introduce pressure and how you can melt rocks just by decreasing the pressure. This diagram here, this is temperature on the x-axis. This is depth, so pressure, because you increase the pressure with depth. And there's a line, which is what we call the geotherm, and it represents the increase in temperature with depth in the Earth's crust and mantle. And it follows a line roughly like this, depending on where you are. It has a different shape in different parts of the Earth. This is our line. And this line here represents the temperature with different depths, so different pressure, at which mantle rock, using this as an example, will melt. Okay? So this is most magmas originate in the mantle. So as you can see here, nowhere on Earth in the crust where the natural geotherm, so the natural increase in temperature, crosses that line to start melting. So you need situations where you either move the geotherm locally or you decrease this melting temperature. And what happens with pressure, say you've got a bit of rock down here and it rises relatively quickly, but with not enough time for it to cool. Eventually it'll cross the line. So any rock which is rising relatively quickly, but not cooling at a strong rate, may eventually cross this, we call this the liquidus. And we end up with decompression melting. Okay? I've talked about decompression before, and we find that at mid-ocean ridges, where the plates are being pulled apart, the mantle is rising, it's losing pressure, and it generates magma. Water does something a bit different. So this is our normal line for dry mantle. This is our normal geotherm. And we've done lots and lots of experiments in the lab. There's lots of experiments in Earth observations where if you dissolve one thing in another, it lowers the overall melting temperature or freezing temperature of the solution. And I gave an example last time of what you do in cold countries where there's a danger of getting ice on the road. You put salt on the road, and then what happens is the salt and the water combine, and overall they will have a lower freezing temperature, so it's less likely for the roads to freeze over. And I'll give you an example of the mineral albite, which is a type of feldspar. There's a famous experiment where if it's dry, it will melt at 1,000 degrees. If it's wet, then it will melt at 650 degrees or something crazy like that, just by adding water. So the water and the feldspar mix together, and you can lower the melting temperature. And this is what happens at our subduction zones. We have a rock here, which is full of water, which is under the ocean. It gets pressurized as it subducts. Those fluids migrate out, and they mix with the rock down here as they're rising. And that lowers the temperature locally, so it changes this dry line to this, because it's now got water in it. So you can cross that melting temperature at a certain depth, so you can generate magma. We call this fluid-induced melting. And you'll see a lot of these diagrams in 203 if you do it. ET diagrams. I've told you that it's quite rare for you to melt that entire rock, and that's because, okay, this is the solidus, the line you have to cross to start melting. This is temperature and depth. This is our geotherm. In this field here, you get partial melting. So you get a mixture of liquid and crystals. Over here is where you get the pure liquid, so you cross the line called the liquidus. It's quite hard to move this line all the way over there, or decrease this line all the way over here, so it's quite rare that we generate entire liquids. So usually we perform this partial melts because we just cross this line, if that makes sense. And another thing, I don't have much time to discuss this, the minerals that are rich in silica, the felsic minerals, will always melt first. So say you have an ultramafic rock and you partially melt it, the partial melt will always be more silica rich than the parent rock. So the parent rock is left more silica poor, and the partial melt will be more silica rich. So from your ultramafic mantle, you partially melt it, you produce a mafic rock, so something like a little bit silica rich. All the silica goes into that melt, if that makes sense. I'll go into that more detail. Willing to say a few more minutes. Simply what happens when you start melting, you get these tiny droplets of magma throughout the solid rock, but those droplets of magma are less dense than the solid, so they rise up through cracks, the pore spaces, and eventually they join together. And when they've joined together to a reasonable size, we call that the magma chamber. So there's a rising mass of magma that pushes aside crustal rocks as it rises to the crust. And it rises because it's less dense than the surrounding solid. And this is just an example of your mid-ocean magma rising between the plates to fill the gap. There'll be a magma chamber underneath the surface, which has risen up through there, and that feeds that volcanic fissure. But deep in the earth, you might just get distributed droplets. So, sorry if the last bit was a bit rushed. We'll go over this more in tutorials and next lecture. But just to summarise, igneous rocks are formed from the crystallisation of magma. Texture can tell you about the cooling history of the magma. So a question in your practical might be, I'll give you a rock and ask you to describe its cooling history. And all I want you to do that in that case is describe its texture. If it's coarse-grained, you can say it cools slowly, it's intrusive. Fine-grained, you can say it cools quickly, it's extrusive. Porphyritic, 2 stages of cooling. Might even get 3 stages of cooling. That's what I mean when I say cooling history. Composition of an igneous rock can be described as calcic, intermediate, mafic, or ultramafic, depending on the relative proportions of light and dark minerals. These have a lot of silica, these have very little silica, these have a lot of iron and magnesium, these have very little iron and magnesium. When magma forms, it's usually by partial melting. The parent rock, which we call, rarely completely melts. We have partial melting. And we're going to continue on more igneous rocks next lesson, and we're going to look at all these different shapes and sizes of igneous intrusion, as well as processes that happen underground. And chapter 4 is what you need to read to understand Earth. I've shared the Understanding Earth textbook with a lot of you that have emailed me. If there's still people who need it, please email me and I'll share it with you. Or come to my office and I'll put it on a memo stick for you. Okay, thank you. If anyone wants to see some colours, they can see some colours.